Okay, hello everyone. Here, what we will be discussing, we will be looking into valence bond theory. Okay, and for the first time, we will see how the coordination compounds or coordinate compounds are formed. Okay, so let's go into it. So Warner was the first one who gave a basic idea about coordination compound, but still he could not answer few basic questions. You can see the first question is why only certain element possess the remarkable property of forming coordination compounds. Second question, why the bonds in coordination compound have directional properties. Third question, why the coordination compound have characteristic magnetic and optical properties. So these were the some of the questions which were unanswered by Warner's theory. So a new theory got developed, that was valence bond theory. Okay, so valence bond theory, it simply says that the metal or the ion which is under the influence of ligand, we are talking about the central metal atom ion, so it can make n minus 1 d ns np orbitals for accepting the electrons, or it can use ns np nd orbitals for hybridization or accepting the electrons. So if it does that, it can give out different geometries such as octahedral geometry, tetrahedral geometry, square planar geometry, etc, etc. Okay, so these hybrid orbitals, that is n minus 1d ns np, or it can use ns np nd orbital, so they will overlap with ligand orbital, and the ligand will donate its electron, and these central metal orbitals, okay, these orbitals, they will accept the pair of electrons. Now you can see coordination numbers 4, 4, 5, 6, 6. So if the coordination number is 4, it can have sp3 type of hybridization. This geometry will be tetrahedral. Dsp2 hybridization, square planar geometry. sp3d, that is trigonal bipyramidal geometry. sp3d2 octahedral geometry. d2sp3 octahedral geometry. Now, note that here sp3d2, it simply means this is your 3s orbital, 3p orbital, 3d orbital. Okay, so they are of the same, okay, same like n is the same. Whereas this one here is 3d orbital, 4s and 4p. Okay, I made a mistake here. It should be 4s, 4p, and then 4d orbital. Okay, that is the first series. Then this is your inner orbital, that is your 3d, 4s and 4p. So that will be your octahedral. It can be different also, like we can increase your principal quantum number by higher values as well. Now this one here is also known as outer d complex. This one is known as inner d complex because we are using inner d orbital. We will talk about it shortly. Now, it is usually possible to predict the geometry of the complex, okay, from the knowledge of its magnetic behavior. So, on the basis of valence bond theory. So, let's look into it. What does the theory say? Here we have an example of diamagnetic octahedral complex. So, diamagnetic means all the electrons are paired. Okay. So, if you see here, we have cobalt NH3 3 plus. So, ammonia doesn't have any charge, it's neutral. Hence, the cobalt here is +3 charge, or it is at +3 oxidation state. So, if it is at +3 oxidation state, you can see that the electronic structure will be something like this. You can see this is your 3d orbital. There will be 6 electrons in total, and 3 electrons are kind of already removed here. Okay, so this is your 4s and this is your 4d orbital. Now, since we know that this is diamagnetic, so what will happen? The hybrid orbital will be made up of this 3d orbital, 4s and 4d or 4p. Yeah, this is also a mistake. This should be np. So ns and np. So ultimately, these two electrons which are present here, they will actually go back and pair in this side. Okay, so these are the 3d orbitals which are paired. Okay, and remaining 2d orbitals which will become empty, they will be used up in hybridization. Okay, So this is your D2. So there are 2d orbital, s orbital, and 3p orbitals are making your hybrid. And ultimately your ammonia, whenever it is coming as a ligand, it will give 6 pairs of electrons in this hybrid orbital of cobalt. Okay, so this is how it is a diamagnetic octahedral complex. So the 6 pairs of electron, one from each NH3 molecule, will occupy 6 hybrid orbital. Thus, the complex is octahedral geometry and diamagnetic because there is an absence of unpaired electrons. So in the formation of this complex, since inner d orbital, that is your 3d orbital, is used in hybridization, so this complex is also known as inner orbital complex, low spin complex, or spin paired complex. Note down the names: inner orbital complex, low spin complex, spin paired complex. So this will be given to you, or this you have to kind of do it in your examination. Next, let's look at another geometry. Paramagnetic octahedral complex, let's say the same example, but cobalt with fluorine, so COF6 3 minus. So here this is your paramagnetic octahedral complex. So paramagnetic means there are unpaired number of electrons. So if you see, if you have the knowledge of if it is paramagnetic or diamagnetic, you can know if it is low spin or high spin. So since it is paramagnetic, so it will be high spin. Okay, so this is your outer orbital because we will be using 4d orbitals. Okay, so in this case these electrons will not pair up. So what will happen, 4s will be used, 4p orbital will be used, and 4d2 orbitals will be used for making your sp3d2 hybrid. Here is again a mistake, it should be sp3d2 hybrid. And fluorine, whenever it comes close to cobalt, what will happen, it will donate its electron in this hybrid complex. Okay, so this is high spin complex, or you can say spin free complex as well. Next, tetrahedral complexes. So tetrahedral geometry is sp3. Okay, so one s orbital and 3p orbital should be involved in hybridization. So if I talk about NiCl4 2 minus, here nickel is at +2 oxidation state. So this is your nickel in +2 oxidation state. Okay, this should be again +2. So 4s and 4p will be making a hybrid orbital, and ultimately you get this as your final electronic configuration, where these electrons are coming from chlorine. So each chlorine ion donates a pair of electron, and the compound is paramagnetic because you can see there are two unpaired electrons. Okay, this one and this one. Similarly, if I talk about NiCO4, okay, is tetrahedral geometry but is diamagnetic. Okay, since nickel is in zero oxidation state and contains no unpaired electrons. Okay, in NiCO4, nickel is actually at zero oxidation state, so no electrons are removed. Okay, so hence this is your paramagnetic, sorry, diamagnetic, because all the electrons are paired. Next, in square planar complexes, that is Dsp2 hybridization. So if you take an example of NiCN4 2 minus, so here nickel is at +2 oxidation state. When it makes the hybrid, it will be making Dsp2 hybrid. So this electron will pair up with this electron here. Okay, and the empty 3d orbital along with 4s and 2p orbitals, it will make your Dsp2 hybrid, and the ligand electrons will be coming up here. Okay, so that is how you will get your square planar complex. Each of the hybridized orbital receive one pair of electrons from cyanide ion, that's your ligand here, and the compound is diamagnetic, as if you see there are no electrons which are unpaired, so hence it is diamagnetic. Okay, now note that the hybrid orbitals, they do not actually exist. I repeat, they don't exist. It's just a mathematical model. Okay, so in fact hybridization is a mathematical manipulation of wave equation for atomic orbitals which are involved. Okay, so it's just a hypothetical scenario that this is what is happening. It's a theory. And that's it. Okay, thank you.